talk to you today about miniaturization. So that's shrinking technology down, making things smaller and smaller, because doing more things in a smaller space is good. I mean, the computer industry is really, really good at doing that, basically because that makes the technology portable and it makes it ultimately a bit cheaper. So let's apply that philosophy to the world's biggest machines, particle accelerators. Now, one of the biggest, most famous particle accelerator that we have in the world, Large Hadron Collider, a colossal 27 kilometers in circumference. That's pretty huge. But there's also other types of particle accelerators that Susie mentioned, for example, that are really important for things like cancer therapy, proton therapy, but they're still really quite large and expensive. So is there something that we can do about that? Can we miniaturize a particle accelerator to something that fits on a tabletop, or even better, in the palm of your hand? Now, if you want to build a compact particle accelerator, you're going to need an immense electric field, because it's actually the electric field that gives energy to those particles, positive particles in this case, and speeds them up, accelerates them to speeds almost the speed of light. Now, the thing is about solid particle accelerators is that they're limited, because as the electric field grows and grows and grows, there's a point at which the actual solid particles will break down and your particle accelerator is broken. But that limit doesn't exist if the state of matter is already broken down. A broken down state of matter is what we call the fourth state of matter, a plasma. A plasma contains electrons and positive particles. It's kind of a cloud of subatomic particles. And now if you bring along my trusty friend, a super intense laser pulse, send it, go straight into that plasma, it'll actually directly interact with the lightest of those particles in the plasma, the electrons, and it'll punch a kind of a concentrated bunch of those electrons forward. Then what you end up with is a whole bunch of negative electrons separated from a whole bunch of positive ones. And in between those, you're going to have an immense electric field. Electric fields that at the moment are kind of thousands, they're tens of thousands stronger than anything that a solid accelerator can achieve. You know what the absolute beauty of that mechanism is, that now something with a solid accelerator that takes kind of like a meter to do, we can do in a millionth of a meter, as a few microns, the width of a human hair. That's the distance over which we can accelerate particles with a laser plasma accelerator. In this case, small is really